let's make a start. So this lesson is going to cover the gallery of graphs type of functions. So we're talking hyperbolas, truncus, and the square root type graph. These are three separate functions you're going to have to be familiar with when it comes to your Saxon exams. So let's have a look. First up, the hyperbola. The general form of it is as follows. It's kind of like a fraction looking graph where you have the x in the denominator of your graph rather than it being as part of your coefficient sequence in a straight line. It's got your dilation factors a and b. It's got your translation factors c and h. Let's have a look at how it all works. So without any transformations, this is what the graph of the hyperbola looks like. It's probably going to be one of the first functions that you come across which have an asymptote. In fact, it actually has two asymptotes. These are the sort of gaps you can imagine in the graph where they both have a horizontal and a vertical asymptote. These are values which are never actually reached by the function. As for why it behaves like this, anytime you have a division where the variable is in the denominator, there's a chance that that denominator will go to 0. Anytime you divide by 0, you get undefined, right? There's no actual value for that. And so for that reason, you can't actually put a specific y value for x equals 0 here, or more specifically, denominator equaling 0. And so for that reason, it is an asymptote. As for why it has the sort of shape that it does, where it's got a positive half and a negative half, you can kind of just figure this out by testing different denominators, different values of x. For instance, any positive value of x, as it gets bigger, the denominator gets bigger, and so the overall fraction becomes a smaller number, right? The y value is getting smaller and smaller over time, but they'll never actually equal 0 specifically, because it doesn't matter how big your denominator is, you'll only ever get closer to 0, not actually ever equal 0. That explains the positive half. Also, why it gets bigger as you get closer to 0. Well, as you start putting fractions in that denominator, the fractions essentially simplify up into whole numbers or bigger numbers, right? Like dividing by half is the same thing as timesing by 2, for instance, which is why as you get closer to 0, it's going to shoot up and up and up. Then on the left-hand side, because you're working with negative x values, you're working with negative denominators, and therefore, basically, you're getting a complete flip of this. On the right-hand side, you had positive stuff. On the left-hand side, you're going to have negatives for that exact reason. And everything else I've discussed is valid as well, as to why it shoots up here and why it shoots across there. Anything at all to clarify further about that? Let's look at some other factors. So the dilation factor, or one of them anyway, the dilation factor A, that is your y-axis dilation. So it's either going to stretch along the y or from the x, depending on how you want to think about that or word it. This is the textbook way of wording things, though both are valid, depending on how you want to pronounce it or write it. If the number gets bigger, it'll go further away from the center. If the number gets smaller, it'll get closer to the axis, because all you're doing is effectively multiplying your y values, so it's got to get further and further away from the center. There is also a dilation factor for the x-axis as well. When it comes to hyperbolas, it's kind of hard to say what's what. Just because it's located here doesn't mean there's not an equivalent way of expressing it in a different, into the numerator, for instance. Like this 0.5 here can be flipped up here for 2. So yeah, we make a distinguishment between x and y dilations, but as far as hyperbolas are concerned, you can write one or the other depending on how you simplify your function. But in the stricter sense of things, we would be considering this to be the dilation factor along the x. More specifically, it would have to appear as a division again, because if we think about fundamentals of transformations, it's anything like affecting the x is kind of opposite to what you think of. You know, x minus h is a shift right, x divided by something is the actual factor itself. That's more about the transformations. That's kind of its own self-contained section in the book. As far as how you actually draw your graph, it's sort of irrelevant what you call it. Reflections are quite similar. In the case of the hyperbola, whether you put the negative in the top or the bottom, algebraically those are the same thing. So a reflection about the y or about the x is going to achieve the exact same thing. If you're starting with the green function, you are flipping either vertically or horizontally. Both of them are the same because they are, I'm trying to call it diagonally symmetrical. It is an odd function, that's the true definition, but you can see how basically whether you flip left, right, or up, down, you achieve the same thing. Also, if you had double negatives, it would flip right back to being positive. So if you reflect in both horizontal and vertical axis, it's the same as if you had done nothing at all. Up until this point, we've only really had one transformation that's actually affected what the graph looks like, and that would be like the reflection. We had the dilation factors, but as far as what you draw by hand, you don't really care how dilated it is. You more so care about the key features and the overall shape. This definitely changed the overall shape if it's negative, because you've got to do it in different quadrants. So too do the translation factors. So, as I was saying before, x minus h. So just like quadratics and all the other functions, x minus a value is a shift right by that value. As for how you actually action that, what you can imagine it as is setting the value of your vertical asymptote. So it used to have a vertical asymptote centered at the origin. It is now shifted right by 1. So you now have this dotted line, x equals 1. And then you just draw it off of that axis as opposed to the origin as your axis. Same thing over here with x plus 2 plus, so you do the opposite, you go to the left of x minus 2, and that's going to set the vertical asymptote at x equals minus 2. Once again, drawing the exact same overall shape, just centered here as opposed to the origin. Any questions there? Vertical translations, again, any plus at the front or back, technically just any plus at all involved in the function that's on the outside of it is a vertical translation. Plus goes up, minus goes down. That's pretty much it. As for how you draw it, once again, we have an asymptote, but this time it is the horizontal asymptote. It used to have a horizontal asymptote at y equals 0. Now it's being shifted up by 1, or in this case here, down by 2. So the combination of those two things, essentially when you're actually doing this, you'll follow this sort of procedure here, where you might have to do a bit of rearranging to make it readable and see what's actually in the function. You can get your asymptotes pretty quickly by identifying your horizontal and vertical translations, and that'll set up the little grid of asymptotes that you need. From there, axis intercepts are solved the exact same way as you would for any other function, with x equals 0 and y equals 0. The algebra for this breaks down into just being linear anyway, so it's even easier than quadratics. And then these are just sort of things you do for any function, which is if you have endpoints, be sure to use them and find them, and then you just, match it all up. That's the overall procedure. Before we get into an example, are there any other fundamentals here that I should... Oh, here's a question. Is it common to get hyperbolas in different or weird forms? Yes. Oh, I wouldn't say common, but it's not uncommon. And it is essential to rearrange them in their general form. Is it essential? I mean, nothing's ever really essential. There's always different ways of doing different things. What you're highlighting here is that sometimes hyperbolas can look something like this. In fact, if we have a look at like question 6, question 5, question 7, they all have the same sort of idea, where the left-hand side is an equivalent way of expressing the right-hand side. When you have this left-hand side over here, you can still solve your x and y intercepts. That's perfectly fine. You're just having x equals 0, y equals 0. Nothing will stop you from doing that. You'll also be able to find your vertical asymptote, because vertical asymptotes will always appear when you have a divide by 0 error. So in this case, a -1 would cause a divide by 0 here. As for your Yeah, as for your final asymptote, that one, you could just imagine shoving like an infinity in these. Nah, they'd be too tough. It'd be a bit challenging to get that final asymptote, unless I'm not really thinking too hard about it. But you'd want to do a sort of conversion to at least get that. But if you're going to do the conversion anyway, you might as well do it at the beginning and then have an easier time of it. We'll definitely have a look at how we do this conversion, but good point that you mentioned it early. For now, we'll go and have a look at the simpler examples. That's more of like an extension sort of thing that might appear on a SAC. Unlikely on an exam, oddly enough. They don't usually... these kinds of graphs are kind of rare for exams because they're usually in a tech-free environment where it would matter. And in tech-free, they typically like to give you circular functions because they're more involved. And yeah, I guess they just don't have anything else that's as involved as a graph, so they tend to use those. I don't know, I'm just kind of making an assumption as to why they're using them. But anyway, let's have a look at an example. So here's a basic hyperbola. It's mostly okay. We just got to do a little bit of rearranging, or we could. Technically, we can again reveal what the true horizontal translation term is in there without doing any rearranging, but it's just a decently good practice to split it up into its general form first. And the reason why we have to change something is because of that coefficient of 2 on the x there. Anytime you have a coefficient on your x variable, it's hiding what the true horizontal translation term actually is. So the first step that I'm suggesting is that you should probably factorize any coefficients that are on the x spot, factorize them out of the function, because now you can see that this is clearly a shift left by 2 plus 2. You do the opposite, you shift left by 2. If you don't want to do that, that's fine. All you ever do for vertical asymptotes is set denominator equals 0. That's true for literally every graph that's ever existed. So if you want a very broad way of finding vertical asymptotes for all graphs, just look at the denominator, set it to 0. But in the case of hyperbolas, we can do a little bit, well, we can do it with less effort. We can just split off a 2 and then see what it is. Which I just discussed, right? You look at your horizontal translation 2 to the left, and this is a vertical translation 1 down. So very quickly we have our 2 asymptotes. Question, I think you might cover this later because it's a bit more basic example. Do you have any good tips, tricks for rearranging, or is it mainly just developed intuition? I mean, it's both, right? I've developed an intuition around it, and whenever it seems appropriate, I do mention different little strategies and things I recommend, just like that, right? Which is, you don't need to do this, but I find it helpful just because it puts it in a form that you're more used to looking at. So yeah, I'm more than happy to keep recommending certain things on the rearranging side of things. Like one of the things you'll see me do often is I'll handle the pluses and minuses first and then multiplications and divides, just because it's more direct. Technically speaking, you don't necessarily have to, but some things are going to be personal preference and some things do actually make you go faster. Where I think it'll make you go faster, I'll mention them, but otherwise, yeah. But okay, so at this point we're looking for axis intercepts. This does just bring it back down to linear. So set y equals 0 for the x-intercept, chuck the 1 over to the other side. I don't actually know why I did it this way. I would have probably nowadays brought the whole denominator over to the other side and then flip things around. But again, you can do things in different orders, right? Divide by 3, multiply by 2. And then, geez, I did this on a lot of little steps, huh? Multiplying x plus 2 by both sides to cancel the denominator. Chuck this bit back over with a multiply of 3, divide by 2, and then subtract 2 at the end. That was a bit verbose. Probably could have done that faster. Like for instance, at this stage here, just write this whole denominator over here, then divide both sides by 2, subtract 2 at the end seems better. Maybe I should write a note for myself to fix that up. It's a bit long. But anyway, ultimately we've now got our x-intercept. X equals 0 for our y-axis intercept, as always for all graphs. For this one, it's nice and easy, right? Sub in your 0, 2 and 2 make 4, and then just simplify the fraction at the end. If you do have a domain, just sub in the end values of the left and right values of the domain as your x values, and that'll get you your endpoints. But we don't have it, which for hyperbolas you pretty much never have a restricted domain. Maybe certain circumstances where you're doing like inverse functions where it might come up, but I doubt it. Other than that, we draw our grid, so the grid of asymptotes, and then we label out the intercepts. And funnily enough, if all you do is that, which is graph out the grid and label the intercepts, you don't actually have to think about what quadrants this graph occupies. If you've got intercepts there and there, you have to draw the curve like that. You can't put it down here, you can't put it up here. You know the graph has to go in this spot, otherwise it'll never touch them. And by definition, because of the hyperbola, it's got to be diagonally symmetrical. You've got to put it over this side again. So if you ever have trouble memorizing like what quadrants it goes in, literally just solving where these are tells you where it's got to go. That's one of the fundamentals there. We'll look at a bit of the endpoint stuff in a minute. I just wanted to clarify if there's anything, well, if I wanted to check if there's anything to clarify here so far. Cool. And if I go too fast, feel free to leave a message or something. I'm happy to double back. This is what I was talking about. If you have a domain restriction, they'll have something like this. X is an element of -3 to 2, -3 being non-inclusive, 2 being inclusive. All you do is, because these are x values, you shove them into the function itself as an x value. Whatever comes out of it is your corresponding y coordinate, and so you just label them accordingly, where the non-inclusive, the rounded bracket, is going to get an open circle, and the inclusive with the square bracket is going to get a full circle there. In practice, if you ever get a restriction on your domain for the hyperbola, it'll likely cut out a full half of it in the context of getting like your inverse functions. I can't imagine really any other scenario where they would do it besides just, you know, forcing you to practice domain related stuff. Oh shit, I did have an example of this. I thought I might have to do it live, but I actually wrote it ahead of time. Nice. Maybe before that though, we'll do one live together, see if you guys can come up with a full solution yourself, and then we'll look at the when it gets a bit more complicated. With that in mind, what I'll do is let's do that. I'll get a screen grab of the summary for the chat, so you can see how or what steps to follow should you wish to. K seems like a decent one. Let's do that. Okay, so that is y equals 1 over x plus 1 plus 3. All right, let's have a think about how we could solve that. In the meantime, I will also pop in the classwork doc for this class. That'll be like the homework that's relevant for this sort of thing. All right, who wants to start us off? Whenever you're ready.
I can start off with the asymptotes.
Yeah, easy. How are we going to get the asymptotes?
So there's a vertical translation of +3, so there's going to be an asymptote at y equals to 3, and it's been translated 1 unit to the left, so there's an asymptote at -1.
Yes, that's right. Awesome. When I'm actually doing it in practice, I'll probably not even bother writing them down and just literally go straight to the graph itself. So you do your little dotted line, x equals -1. You do your dotted line, y equals 3. Nice. That gets us our grid of asymptotes. What else do we need?
We can check for reflections or dilations.
Yep. Anything of relevance?
No.
That's correct. Yeah. No negatives, no multiplications anywhere. Cool. As far as it informing your ability to graph, dilations, kind of whatever. Reflections, yeah, if you wanted to know ahead of time what the shape looks like, it can be a nice little error checking thing for yourself. But if all you do is go for your x and y intercepts, that will by extension show you what the graph should then look like. But yeah, both is valid. Speaking of which, that means getting our x and y intercepts. Broadly speaking, how are we doing that?
To get the y-intercept, we set x to 0, and to get the x-intercept, we set the equation to 0.
That's it. Yeah. X equals 0, y equals 0. So let's do our x equals 0 first. And then our x equals 0. Oh, sorry, I did that one. 0 equals 1 over x plus 1 plus 3. So yeah, nowadays, subtract the 3 both sides, multiply both sides by x plus 1, put the 3 back over as your division of negative, and then subtract 1. So that'll be minus 4 on 3. Actually, let me break that down one step further. So x equals minus a third minus 1. You would then, I know some people have a bit of trouble with fractions, so split that up into a fraction with same denominator, and now the denominators are the same. You can then combine those together. X equals negative 4 thirds, which is a little bit bigger than negative 1, which is going to put it here. And then, yeah, now that we know we have a cut there and a cut there, that already tells us our graph has to go over here and over here, ideally with a better curve than that, but yeah. As for the error checking, yeah, we then look and see there's supposed to be no reflections, so we already know it should be in quadrants 1 and 3, and I say that with air quotes because technically the quadrants are related to the xy axis. You know, I mean like top right, bottom left for the basic hyperbola. Yeah, that's about it really. As we can see, there's also no domain on this, so nothing else to really do here. Sweet. All right, back to the screen share. We're going to have a look at the what I've referred to as a non-typical hyperbola. There are a couple of ways to handle this. Ultimately, our goal is to take it from linear divided by linear into only having a linear on the denominator and splitting up the rest of it into whole numbers and coefficients. You can do this with raw algebra, where one thing you can do is rewrite your numerator a bit more strategically. Like, for instance, splitting this x plus 3 into x plus 1 plus 2, because 1 and 2 make 3, and then splitting things off from there, because that way, when you split it off, things cancel down. That works fine. In fact, it's probably the preferred method of doing things if you have strong algebra and strong foresight. What I'm going to show you is a little bit longer, but it's a completely repeatable process, and it uses something that you should know by this time in year 11 anyway, which is your polynomial division stuff. So this is a division of polynomials. They are monic polynomials, degree 1, but they are still polynomials. So when in doubt, if you're struggling to find the algebra to make this look like that, then polynomial division works. You take the denominator bit, chuck it out here, take the numerator, chuck it on the inside. We'll do a quick recap of it. It's not going to be super relevant for those who haven't done it for a while. Basically, you take the two leading terms and divide them by each other. This one divided by that one, and then you put the result on the top. Then, once you have that result, you take that and multiply it through by the entire denominator. So 1 multiplied by all of that, whatever that comes out to be goes on the bottom there. Then you perform a subtraction, so you wrap this thing around in brackets and subtract it from what's above it. X minus x equals 0, 3 minus 1 equals 2. This is considered the stopping point of polynomial division when you have just an integer at the end. The way you finish it up is you have the quotient, the thing on the top, it's going to be there. The remainder is going to go on the numerator of this denominator. If you haven't done polynomial division for a while, don't worry too much about doing this. It's a bit beyond the scope of this lesson because we've still got a couple of other graphs to have a look at. Just know that it's there if you need to do that. That's one way of doing it. I'll quickly show the algebra way of doing it. It does require a bit more foresight, though. Now, I don't have that one written up, so we'll do this on the handwritten section. So basically, you would have a graph of x plus 3 over x plus 1, and because you're trying to cancel something down into an integer, your first goal is to figure out how do I get the denominator into the numerator. And it's already kind of there, right? This is just 3 bigger, well, technically 2 bigger than that. So start by splitting up that term into 2 separate terms, and then split that off. So x plus 1 over x plus 1, and then 2 over x plus 1. They'll have the same denominator, so what I've done is just split that one off to its own separate fraction. From here, anything divided by itself is 1, and that gets you exactly the same spot that we had at the end of our polynomial division. So as you can see, faster, but what you're actually doing will differ depending on your denominator every single time. Up to you. Both of those work. Yeah. Do we want to practice one of those? It's very similar. I'm just trying to think we have time. We're about halfway through the lesson now. The only difference is, once you get here, then you treat it exactly the same as the other example that we just did, right? Find your asymptotes, x, y intercepts. The only thing you might want to practice would be the simplification steps. Does anyone want to see that, or should we move on? Cool. Truncus, a very similar graph. You'll notice it's almost identical, with the exception of the fact that the x term is now squared, and any of the factors involving the x are squared. So what's going on? A similar shape, actually. You can think of it as a hyperbola that's been flipped up on both sides. Right? So not only do you have the first quadrant, but you now also have the second quadrant. You're taking this part of it and then shoving it up here. It does also come a bit more narrow. That's because you now have x squared. So basically, for every unit that you go to the right or left, you're also then squaring that number. So it's traveling a lot faster than the hyperbola does. That's more just for graph theory. As far as sketching it, you don't really give a shit. You just want to draw the overall shape and then call it a day. But, for your own understanding of why the graph is doing what it's doing, that squaring term is making it accelerate a lot faster, which is why it tends to have a bit more of a steeper climb and a steeper fall. The other bit is, why is it now both positive? Well, whenever you square a negative number, that number goes to become positive afterwards. And so for that reason, I have just noticed that I didn't actually update this. I kind of just copy pasted it. Oh no, that's awful. I should have had them squared to show that they go positive again. Anyway, like for instance, -1 squared goes to +1. So it's going to go right back to being a positive number. Dear, I've got 2 things now to update. Slacking. Dilation factors are working the exact same way as they did with the hyperbola. Bigger number on here means it goes further away. Bigger number down here means it goes closer. So there's a 3 there, it's going closer. Again, this doesn't really inform any decision making, unless for whatever reason you had to put them both on the same axis. Then the reason that I'm really mentioning this is because in your investigation SACs, a lot of the time they do ask, hey, what's this term do to the graph? What's that term do to the graph? and you'll have to be able to answer those kinds of questions. Reflections, so because this is now, no, it's the same thing actually, even if you had double negatives. No, sorry, I'll change my mind again. It's a little bit different here with reflections now, where you don't actually have that diagonal symmetry anymore. So now, as far as reflections go, the only thing that's actually possible is a reflection about the x, right, flipping vertically. Because when you put a negative sign as a reflection for your, for your x reflecting about the y-axis, it actually goes inside the square. Right? You want to attach it directly on the x variable. Kind of like how if there were numbers around it and pluses around it, you would still put it on the x. This this square is also a thing that's involved there, so it's got to go inside that bracket. And so when you actually resolve that, as we just discussed, squaring a negative number brings it back to being positive anyway, so the reflection kind of just fizzles out. Horizontal translation, vertical translation, it's exactly the same as the hyperbola. Right? This is shifted right by 2. The only thing that looks a little bit different is that it's squared. But again, all you're looking for is what's minused and what's plussed. That's all that really matters. Vertical, exactly the same as well. They still have the same number of asymptotes. They still both have a vertical and horizontal. It's just what quadrants you're occupying is the only thing that's different. And because they're so similar, you literally use the exact same procedure, right? You're getting your asymptotes from the horizontal and vertical translations. You might have to rearrange things a little bit. And yeah, axis intercepts solve the exact same way as well. We didn't talk about too much difference, so we could probably dive straight into an example. If not, let me know and I'll double back. So just to be difficult, I've given us a truncus, but not a really nice truncus, one that's got some rearranging to be done. If we have a look at the actual book, they pretty much never do this. In fact, they even show you, if they do it, they say, hey, this can actually be this. They're showing you how to go from, or at least showing you that you can go from one to the other to make life a bit easier. Again, the same rules apply. Any coefficients on the x are ideally factored out, and in fact, even more ideally factored out of the square as well. So you can take the coefficient of 3 off of these terms, but that still keeps it in the square. Taking it out of the square, you have to square it on the way out. Again, that's just to make it look a bit neater, so we know it's more familiar to us. We can now see +2 means a shift left by 2, and this +2 means a shift up by 2. One of the things with the truncus is that it's more likely that it won't actually have any x-intercepts. With the hyperbola, because it had 2 sections on top and bottom, it made it easier for it to have both. When it comes to the truncus specifically, if it's vertically shifted and pointing up, none of its tails are touching the x-axis. So this is where what Nihal was doing before, which was looking for any reflections. This is where looking ahead of time to figure that out can be helpful, because if you do go ahead and try finding something that doesn't exist, you might confuse yourself for one, or worst case scenario, you're just wasting time, which still isn't great. So understanding that this is a positive truncus, it's going to point up, and it's also being shifted up by 2, means we shouldn't bother finding an x-intercept. But just in case you do, here's what it looks like. You set your y equals 0, subtract both sides, do your division. This isn't even correct. Dear God, how long ago did I write this? Oh, wait, no, it is. Sorry. Divide by 2 and multiply by 9. Okay, I'm not that bad. Keep simplifying, and you get to this stage here where you're like, oh shit, to expand this any further, or to simplify this any further, I would have to square root both sides, but I am not allowed to square root a negative number, unless, of course, I'm in Spec Math, in which case you can, but yeah, we're not in Spec Math here. So, if for whatever reason you get yourself into this situation, one of 2 things. One is it just flat out doesn't have an x-intercept, which is ideal, or 2 is you've made an error in your calculation. In both cases, just go back, have a look at this and be like, okay, it's shifted up by 2, it's positive, right, doesn't actually have 1. Got it. Y-intercept, it's pretty much always going to have 1. If we look at how the truncus actually looks, the only time it won't have 1 is if it has 0 horizontal translation. Any shift left or right will make it touch the y-axis at some point. So it's pretty likely it's going to have it. X equals 0, simplify. And yeah, again, just dotting it out like we did before. We use the asymptote grid that we had. We mark out the intercepts, or I guess in this case, intercept singular. And yeah, label the graph. Any questions there? Okay, cool. This again was just if you have a domain restriction, but it's the same thing, right? Just shoving your x values into the x spot, get the corresponding y's, and you're sorted. There is a bit of wonkiness that goes on around here, which we'll discuss in a moment. More so these two, actually, 4b and 4c. We'll do one of the much more standard ones first, and then we'll move on to what's going on here. Because these aren't really truncuses anymore, they're a little bit different. Okay, let's try 1h, I guess. The procedures, in fact, the procedure's literally identical word for word, so I don't even have to, I don't think I have to send another screenshot for you to look on. The only thing that's a little bit different is the general form of it has a square instead of it just being linear. I don't even know why I'm copying one down. I should just be able to make one up. Anyway. Cool. All right, let's smash through this one. Should be basically the same as the hyperbola. What are we going to do?
Start off with the asymptotes again.
Yep, asymptotes. We can pretty clearly see what those are going to be. There's no like further rearranging to be done. What are we going to have?
Y equals to 2 and x equals to 4.
Y equals 2, x equals 4. Yep, y equals 2, x equals 4. Easy. 2, 4. Cool. What else do we need?
There's no dilation or reflection. It's on the x-axis, so it doesn't matter.
We do.
Sorry, the y-axis.
Yeah, so we do have a reflection. That will actually inform a bit of decision making, because if it was pointing upwards, we wouldn't have any x-intercepts, but because it's pointing down, we will. But yep, it's still fine. Which, yeah, leads us on to solving the x and y intercepts. This is the same as before, right? X equals 0, y equals 0. So maybe I'll just do that down here. Y equals -1 on, so -4 squared is going to be 16 plus 2. That's kind of nasty. 1632 minus 1 for 31. Yep, that should be good. Does that actually make sense? 31 on 16 is a little bit less than 2. So yeah, that should make sense. And then the y equals 0. So 0 equals -1 on x minus 4 all squared plus 2. Yep. Minus 2 equals -1 on x minus 4. Just bringing that 2 over. Flip these terms around. So multiply by x minus 4, divide by minus 2. Going to have x minus 4 equals -1 over -2. x equals half plus 4. So that's 8 on 2, so 9 on 2. Again, is that going to make any sense? Yeah, 9 on 2 is a bit bigger than 4. Should be. So, yeah. Let's put it there. Oh. Yeah, let's not be stupid. Let's fix that. Anyone know how you would spot that error? Like, I know I made it, right, and I spotted it. I did forget to put the square in there. Any idea how I would know that I have to go back and fix it without, looking at my working? Anyone know what I spotted there? Because I didn't look at this, clearly. It's a similar idea of looking ahead and expecting, okay, how many solutions do we expect to have? What I saw was...
It's a truncus, so
yeah,
there will be two solutions.
there's going to be two solutions, that's right. So when I drew that out, I was like, okay, cool, we're going to have this, and we're going to have this. Oh, what's this one? Nothing there. So I knew it had to go through there, and therefore had to come through here, which meant I'd made a mistake somewhere. So these are little error checking things that you can do yourself. So that means all of this needs to fix up a little bit more. So square root of a half gets you plus minus a quarter. And this should still be the x minus 4 over here. And now you're plussing 4 onto both of those. So for the sake of readability, what you'd probably do is split this into two separate equations. You'd have x minus 4 is equal to positive a quarter, and x minus 4 is equal to negative a quarter. If you're really, really good at math and doing it fast, then you can just sort of envision both of those at the same time, but I wouldn't be testing those things in a real exam. X equals a quarter plus 4, so 4 4s are 16 plus 1 gets you 17 on 4. And then the opposite, so 16 minus 1 gets you 15 on 4. And then we've got to update these. So that was 17 and 15 on 4. 15 on 4, 15 on 4. And then, yeah. Oh, that got a bit blurry there at the end. Cool. Any questions on that one? Slightly more challenging, just because you're working with a little bit tougher algebra. But otherwise, yeah. Okay. Next up, so I'm going to briefly touch on question 4B specifically. It's a CAS related thing. This isn't something you have to know how to sketch by hand or anything like that, but I just think it's nice to talk about your theory of equations type things for your investigation stack, should it be relevant. So there's a quadratic on the bottom that does not make it a truncus necessarily. What we're going to actually end up seeing, hopefully actually, hang on, I might have to double check this because this might be a perfect square. Let me draw it first to see. I'll make up my own if I have to. We had 2 over x squared minus 6x plus 9 plus 2. Yeah, okay, that was a perfect square. Not a good example. Basically, to make this into a truncus again, you would want to factorize this using your add together times together. I saw the 6 and the 9 and I thought that might be the case. The 8 and the 16 for the other question is probably going to be the same thing as well, to be perfectly honest, but let's find out. Because I do want to show something kind of cool. No, it's not going to do it. All right, you know how we fix that? There we go. So we have now achieved a graph that looks, it has some resemblance to the truncus, but now we've got a couple of asymptotes going on there. Got this sort of quadratic kind of shape going on there, and then like a hyperbola kind of, well, maybe a truncus thing going over here. Before I explain what's going on in this kind of graph, does anyone want to take a stab at why what's happening is happening? You got the graph that's the function of it is here. This is more so going to be on like theory of graphs.
Is it got something to do with the fact that it's a quadratic on the bottom?
Yeah, certainly. What can we imagine that the quadratic on the bottom, this being a different quadratic, not a perfect square, I mentioned that a couple of times. Why is it that a different, non-perfect square does this?
Is it because for certain values, if you just look at the quadratic itself, it will have x intercepts at those area, so that means the y is 0,
Yeah,
and we can't divide by 0.
yes, that's exactly it. I said at the beginning, asymptotes, specifically vertical asymptotes, are always given by the denominator being 0. This quadratic has two solutions, and because it has two solutions, it goes to 0 twice, right? It's going to go to 0 whatever this spot is here, and it's going to go to 0 whatever this bit is here. For that reason, you get your two asymptotes. As for the rest of this bit, that's kind of a bit harder to describe. It's more so just going to be where is it net positive, where is it net negative. That's a bit more of an in-depth discussion. I just wanted to sort of highlight, hey, this is a graph you don't necessarily know, but you can use some learnings from how asymptotes work to make some interpretations of it. Cool. Okay. Next up, we should have enough time for this square root graph. Okay, so the square root graph is going to actually be similar to the quadratic than any of the other graphs that we've just looked at so far. What you're seeing here is the fully transformed state with all of the different coefficients. As far as the base version of the graph, it's going to look like that. It's going to be sort of like this tick going on to the right-hand side, up and to the right, with a sort of concave down approach to it. What you're essentially seeing is half of a graph. So this one isn't necessarily in the study design, but it's worth understanding because it teaches you a bit more about why the square root graph looks the way it does. This is not considered a function, it is considered a relation. The difference being that functions can only ever have one y value for any given x, whereas this one, let's say for instance x equals 2, that has two possible y values. This one over here, only one possible y value for the x. That's the difference. Relations are pretty much very rarely taught in methods, if at all. They're kind of just there in the textbook to give a bit more detail as to what's going on. This is the graph of y squared equals x. It is a parabola on its side, basically. Kind of like how you have y equals x squared goes up, the y squared equals x goes right in this case. All the y values getting squared and the x's are maintaining the same. So, how does that give this? Well, when you square root both sides of this equation, you would now get plus minus square root of x. Where is it? That's plus square root of x. That's minus square root of x. So you get two halves of the function. As far as methods is concerned, we break that, two halves of a relation, I should say. And as far as method is concerned, we only really ever care about one or the other. So the positive half is given its own function, the negative half is also given its own function. You will only ever draw which one you're actually given. If it's a negative sign at the front, you obviously draw the negative bit. If it's a positive sign, or well, more technically, it's going to have nothing at the front, you would draw the positive half. So that can help you get this shape down a bit. It's basically just a parabola on its side, and you erase the part that you don't want. Yeah, okay. Dilation factors, again, so multipliers make it go bigger. Dividers will make it go longer. Reflections, we just talked about that. This one does actually have a reflection about the y-axis, which at least initially seems to break a rule of how graphs work. How is it that we're allowed to square root a negative number? In reality, we are not square rooting a negative number. We're square rooting a negative variable, and those are different things. Square root a negative number would be like trying to square root -4. Bad. But when you have x as the negative, it means that when you sub in a negative value for x, you now have two negatives in that spot, both of which will now flip to being positive, which is why this graph can only ever be valid for the left-hand side, all the negative x values, rather than the right-hand side. So you can actually have negatives on the x because that is allowed. You're allowed to have variables be negative. You just can't have the net number be negative. Which also explains why this graph doesn't exist on the left-hand side most of the time, right? Any negative x values going into either of these would break the graph, so it's undefined from anything left of 0. Translations, we've seen this enough, right? So basically, what the translation is doing is setting the little vertex, the starting point of the graph. So this is a shift right by 2, x minus 2, shift left by 1, x plus 1. Vertical translation shifts the vertical component of the vertex. Plus 1 goes up, minus 2 goes down. The procedure looks, again, very similar. Oh, yep, Taihan.
When you're sketching it, what are the kinds of points? Do you need to plot any points on the graph apart from the intercepts for square root graphs?
Yeah, you need the vertex. So
Right.
vertex plus intercepts. So that's going to be endpoints. This is one of the points where you always have it applicable. And axis intercepts. Those are the only things.
Yep. So it's not necessary for like any other points on the graph itself, just those ones.
Yeah, so basically, in the case of this blue f of x, you want this and you want this. We'll see later on we'll have both. Oh, actually, this one only has one. Point is vertex and both intercepts, if they have two of them. Nothing else would be a key feature there. So let's see how that works. Again, I've given you a slightly nasty one. Just factorize the coefficient off. If you want, you can take this all the way out. You would have to square root it on the way out, and that makes it a little bit weird. -2 root 3 seems a bit strange to do. But again, it's just sort of whatever. Just there to make life easier. So if you think it looks easier that way, feel free to do that. I personally like to look at this a bit better. I can see what's going on a bit more. Okay, so just like how we looked at the translation terms for our asymptotes, we're now going to look at them for the x and y location of our vertex, shifted right by 1 and up by 1. So the net coordinate is going to be 1, 1. And you would dot that out. It's going to be inclusive. Whenever there's no domain given, 1, they were just lazy and didn't write the question properly. Or in my case, I just wrote it a while ago, like really early on in my career. When there's no domain, they just assume it's all the maximal domain. And then axis intercepts. So once again, looking at the overall shape of what's going to happen, we have a reflection involved. It's a reflection pointing it downward. So normally it would go up and right. Now it's going to go down and right. And since it is shifted to the right and up, we now know it's going to start in quadrant 1 and basically shoot down to quadrant 2. 4, sorry, that's what that is, 4. So, knowing that that's the rough shape of the graph, I'm not going to bother looking for a y-intercept. I can see it's not going to happen. If you do, for whatever reason, you're again going to... no, there is a bit of weirdness here. So this one is the nastiest thing. This is the second reason why I bothered to mention the y squared equals x graph, that relation. If you try to find the x-intercept, you will. Oh, sorry, what am I looking at? This is a different graph I'm talking about. My apologies. There will be a bit of weirdness we'll look at later. I thought it was going to cut now, but it doesn't. Keep that in mind though. Even if it doesn't have an x-intercept, when you try to solve for it, you'll find it. We'll look at that in a minute. But in this case, it's perfectly valid. We're supposed to. For y-intercept, we kind of know it's not going to happen. Square root -3 already will tell us for sure not going to happen. So label the x-intercept and then draw the curve accordingly. I know I kind of got ahead of myself there a bit, so if there's anything I need to clarify about that, let me know. Okay, cool. This is just talking about the domain restrictions. It's the same for every graph ever. Here's what I wanted to talk about, a bit of weirdness. So why is it that we can sometimes get a false positive? Why do I find an x-intercept when I don't actually have one? Very basic graph here. It only has a vertical translation up by 1, which normally would imply that it doesn't actually have an x-intercept, right? It's going to start above the x-axis and it's going to point up. Should never touch. Why then is it that when I try to find an x-axis intercept, I get it? 0, so take 1 on both sides, square both sides. That gets me x equals 1. I know the picture was there. Does anyone want to take a stab at why we get a solution here when we shouldn't? The picture I had was a bit of a hint, which is why I'm not going to show it again. You've come off mute, but I'm not hearing anything just yet. Just in case it's an audio thing. Still nothing, unfortunately.
I think it was like kind of just off the point a little bit.
Just off the point a little bit. How do you mean? So we've got this solution. Why do you think it's come up? Got to do with the y squared equals x graph.
And
maybe it's my Wi-Fi then, is it? You're kind of cutting out as well. Is everyone else hearing each other? I didn't quite hear that. Okay, I'm hearing things now. Let's try again. Sorry, I think my Wi-Fi might have dipped for a bit.
y-intercept and x-intercept.
Yeah, okay. Hopefully this sticks to landing, because I'm hearing you guys come out a bit buggy. Let me know in the chat if I'm coming out as buggy. We'll just explain it now. So with the y squared equals x graph, it was a relation. In methods, when we're handling these things, we only care about the functions. So essentially, what you're doing is finding the x-intercept of the other part of the graph that we're not supposed to have. So this one only had we only wanted to have the positive part of the square root. But when you go through the math, root x is like, when you square both sides for your algebra, the algebra isn't taking into consideration that you only wanted one part of it, which is why you're finding the this sort of ghost part of it that's left over. So this, more than any other graph, you want to keep track of, do I want the positive half or the negative half? Hopefully that came through. Let me know if there's any questions about that. We're about to hit time anyway, so I might even, if there was any issues with that, just let me know. I'll point you in the right direction for a video of some sort. Yeah, about 20 seconds left, so if there's any further questions, feel free to let me know. Otherwise, I'll give you a very brief break. Very brief early finish.
Thanks, Chris.
Thank you.
Thank you.
Thanks.
Can I? Oh, it's finally working.
Oh, it is now? Yeah.
Oh.
Cool.
Yeah, I think my microphone died.
Yeah.
Unfortunately.
Damn. Did you have an idea?
Yeah. So I was looking at like how to visualize unconventional graphs. So like in geometry.
Yeah.
Well, x squared can be visualized with a square, and x cubed can be visualized with a cube.
Sure.
What about something like 1 over x? Well, that
Yeah,
kind of
so
looked into, like, you can use the graph as a visualization. You can look at you can consider a square or a rectangle from the origin to the and the top right wait yeah, top right will be on the graph. So whatever the area is, it like of 1 over x, that's it's going to equal to 1, and whatever the change
oh
is
yeah,
will be
yeah,
equal to, like, whatever we take away from the top should be added to the side, so the area always stays the same.
yeah. I get you. That's definitely a unique way of looking at it. I wasn't
Yeah.
that wasn't supernatural to me, but I do get the idea of what you're looking at there. Yeah, because you got that sort of that's like a property of it being diagonally symmetrical, which is kind of a term I'm just making up, but yeah, having the fact the area is overall net maintained. That's a pretty cool way of thinking about things. Yeah.
Yeah.
For myself, when it was these kinds of graphs, I would usually just sort of plug in a few main points and being like, okay, what happens when x gets bigger? What about smaller? What about negative? And just sort of going from there.
Yeah, I'm wondering if we can visualize something like square root of x.
Visualize something like square root x. I mean, that's kind of what I was leading into with the y squared equals x graph, relating it directly to the quadratic, but on its side, and then you just take one of the portions of it. That's how I've personally been visualizing it. I'm not overly familiar with the way you're using with like areas and stuff like that to help visualize things. So that might be more of a you thing to try and like Wikipedia or Explore or something like that, YouTube. But for myself, it would be something like y squared equals x is just the quadratic on its side, and then you just take one of the portions.
Let's see. Okay. I mean, I was just I've got the idea from like Tree Blue One Brown video.
Oh sure,
So,
yeah, okay, that checks out. Then they usually do these nice little higher level math stuff explained in a simple way. I do like that channel. It's
Yeah.
good, isn't it?
Yeah.
Sick. Maybe they'll have some stuff on that then. I'm sure if you search on the
Yeah.
channel, you'll find a whole bunch of stuff that's kind of cool. Nice.
Yeah. Okay.
I'll leave you to it then, mate.
Can I just ask you one more question?
Oh yeah. Yeah, sure.
Well, you were a firmware developer, right?
The job title was firmware engineer specifically, but I did some
firmware
coding related
engineer.
stuff.
So, did you always want to be like in that field, or?
Good question. So in the literally at the end of my VCA year is when I was like, cool, I like physics. I did well in physics. I did well in math. What happens when you put physics and math together? You do engineering. And so I was just like, yeah, why not? Engineering seems good. On my preferences, I had put civil, electrical, and I literally can't even remember the rest. It's probably just also civil and electrical, but in different universities. I put like my Monash, the RMIT, whatever I could get. I actually did end up getting an offer for Monash specifically, and then I drove there, and it took way too long. So I was like, nah, I'm not doing that. Go to RMIT, way quicker. I ended up choosing specifically electrical because I thought it was electronics. I later found out electrical is about your power lines and power generation. So I moved into the electronic side of things. So it's not something like I knew ahead of time I wanted to do. I had no real thoughts as to what it was. I just knew that if I did these STEM related subjects, I would find something that would be worthwhile in the world. Because, all it's always going to happen is technology is going to increase over time. And if you're good at STEM, you'll have a place in that world. So that was the overall idea. As for what it looked like, it was kind of squiggly, right? second year of uni, I transitioned from electrical to electronic. It's a fairly easy enough switch to do. A lot of the subjects did overlap up until that point. And, you know, you just find things that you like in your courses, you find things that you don't like, and you just sort of, because you'll pick a fair few electives. Most universities will have at least some electives for you to choose. So in that way, you'll still be able to craft things, even if you don't necessarily know exactly what you want to get into right now, because I certainly didn't until literally after my last exams.
Yeah. Let's see.
Fair enough.
Okay, so yeah, okay. Thanks.
Yeah, no
Have a
worries.
good day.
Happy to support. You too, mate. Take care.